Alright guys, welcome back to MECH2320. We're going to go through chapter 31 here. We're going to be talking about wound rotor motors. Okay, these are AC motors, alright, so it means we're changing, the fields and things like that to force the rotor to turn around. We got to communicate through slip rings. Okay, so we just want to, identify some basic characteristics. Some of the stuff that we've talked about already in previous chapters about controlling it are going to come out again, alright, so hopefully those things will start to solidify and sink in as we go through these. Okay, so if we take a look at a wound rotor, so here the picture in the upper right hand corner, that's a wound rotor, and it's very easy to identify because we have slip rings. Okay, so the slip rings are how we actually maintain connection with the rotor as it's rotating around. Okay, and I've shown you guys one of those in class as it's rotated around. All right, the wound rotor, that was one of the first alternating current or AC motors that was available and created for speed control. But it also does have an advantage. It's a high starting torque. All right, we're going to talk about that a little bit when we get into where the resistors are and that sort of thing and how we start it up. But when we talk about the rotor winding here, okay, on the wound rotor, it contains the same number of poles as the stator. All right, so the number of poles in the rotor, right, the rotational piece, and has the same number of poles as the stator, the outside, the stationary piece. Okay, now we are able to start these up. We use the variable resistor method. Okay, so remember, we use resistors to control the inrush of current at the onset of energizing the motor. So we do that, and notice the resistor symbols on here have an arrow going through them. That means they're what? Variable resistors when we do that. So the fact that we also have variable resistors on here, okay, it means that we can use that resistance for startup, and we can use that resistance to control the speed. So since it's a variable resistor. Okay, so main factors here and for the induction motor is that we have what? The stator and the magnetic field strength, that's important. The the rotor magnetic field strength, and then the phase angle. That's the difference between the rotor and the stator flux. All right, remember we're talking the magnetic field strength here. So those are what's really going to determine the amount of torque that we have. But remember, we're controlling the magnetic field with resistance and the amount of current that's allowed to flow through the windings. Okay, so it all kind of goes hand in hand, but we're controlling that current with the variable resistors, so we can control the difference in the magnetic field strength. So that's how that's really going. Okay, so in those resistors, when we start with them, right, we're controlling that inrush current. That's really what increases our torque. All right, that's why our starting torque is very high. Our speed will be very low, but our starting torque will be very high, even damaging where we can crush gears and that sort of thing. So we got to be careful with some of the starting torque on these. Okay, how do we create maximum torque? Okay, that's when our stator field and our rotor field are in phase with each other. Okay, that's when we're at maximum. If we were to take two bar magnets here, and that's kind of depicted in the upper left hand display, right, those magnets are going to be at their strongest when they are right next to each other, perfectly aligned, right? North and south are perfectly aligned for it to attract one another. But if we make a small angle that's off, okay, one is going to lead the other. One will be stronger than the other. But when we're able to perfectly align them, okay, we'll be at our maximum force. And that's really what we're doing, with a rotor and a stator. We're creating the magnetic fields there. Not physical magnets, right? But same exact concept. Okay, so that's how we get maximum torque out of that. All right, here's the schematic symbol. So when you guys see a schematic and you see this one, you are going to know that it's a wound rotor induction motor based on just what you're looking at. Now we've talked about this stuff in previous lectures, so I am going to go through this one a little bit faster. Manual control of the wound rotor. How do we do that, right? We have push buttons and all those different things, and we can control the current, which in turn controls the speed, because the current controls the field, or the magnetic field in the stator and the rotor when we do that. Okay, so by changing the resistance, we change the current, and by changing the current, we change the magnetic field, which changes the speed as it's going. Okay, now with the small wound rotor motors, those are controlled by a make or break rotary switch. Okay, remember, make or break means it makes the connection before it breaks it, and we have a rotary switch. So think of like your fan or something like that. So the contacts, okay, and you can have as many contacts as steps of resistance. Okay, so we'll look at a schematic here, but say we want 4 steps of resistance. We're going to have a contact for all 4 of those different resistance values. Okay, so if we take a look, here's kind of the schematic of what's going on with that. So we can see that all the resistance is varied, right, based on the M1, M2, and M3 connections here, okay, for the phases. So as we take a look at those, and as we turn the knob, okay, on the switch or on the rotor, as we adjust them, okay, now when we adjust these, the way this one's set up is they're all going to get the same amount of resistance at the same time as we adjust these. Okay, so what we have on though is a micro limit switch, and that's used to detect the maximum resistance for us. Okay, and these motors won't start unless the resistance, okay, is all in the rotor at the beginning. Okay, and then we swap that over to control everything so that we can get maximum torque or speed or things like that. Okay, we can also do it with time controlled starting, very common here. So we just use our time delays, and we've talked about all those before, and just kind of depends on the number of steps that we want to take. So right here, we're using timers, okay, on delay timers to start the motor up in certain speeds. So this is like ramping something up. So we can see how there's 1, 2, 3 timers on here, right? Each one of those timers connects to S1, S2, and how we close those, okay, controls the amount of current getting to that motor. So that's how we can bring that up to speed as well. So if we close S1, it's going to change the resistance going to the motor. If we close S2, then it changes the resistance. So as we're changing the resistance, we're changing the speed and the magnetic field. All right, and we can look at the whole system here. Okay, this is how it would lay out. I'm not going to walk through like step by step on the control system piece of this. Okay, you can look at the power piece up, showing where S1, S2, and our speed control. That's why we call it S1, S2, S3, and how we control the speed through changing the current through the resistors. Okay, and we can change it based on time. So the motor needs to get up to the right speed. It's not going to go from 0 to 60 instantaneously, or whatever speed we need to get it to, right? Or 0 to 1500 RPMs, or 0 to 27 RPMs, or something like that. We gradually get it up to that speed. Okay, so we can do this with all different timing. Very common methods here as we take this approach. Okay, most common method I would say in this case though is frequency control. Okay, where we vary the frequency. And when we're changing the frequency, what we're doing is changing the induced voltage. Because remember, our current and our voltage, they're coming in at the sinusoidal type wave, right? It has a frequency that's tied to it. And it has a period. And we talked about all of that in the electrical class, right? We did a whole bunch of different signal analysis where we could look at the amplitude, we found the period, the frequency, and the relationship between the period and the frequency. Okay, so very, very, very important. And we're going to actually do a lab on this where you guys, you're going to use a VFD drive, a variable frequency drive, and you're going to be able to change how, manipulate the voltage through the frequency, and you're going to be able to control the speed there. So we're going to have a fairly in-depth lab when you guys go through that one so that you really kind of understand. Very common, very easy. You have a VFD that you're just going to program and do different settings to. Okay, and what are we affecting there? We're affecting the slip. Okay, what's the slip? All right, that's the difference between the rotor speed and the synchronous speed. And we generally tend to do that as a percentage. So like a 5% slip or a 3% slip or something along those type of lines, when we're doing that calculation. So that's really what that is. Just remember the slip is the difference between the rotor speed and the synchronous speed. And remember, when those two speeds are aligned, that's when we're at maximum torque as well. Okay, so very important to kind of understand those concepts when we're talking about a wound rotor. Okay, and then just lastly, if we're looking at a variable frequency drive and how that impacts it. Notice we still have the resistors here to change the speed. Okay, but notice we have S1 and S2 activated now on here. There's a control piece that's directly on the motor. So notice that's kind of separate where that VFD drive actually sits on the schematic diagram here. So, but guys, we're going to get a lot more in depth on VFDs. We'll have a separate lab, separate trainer just for VFD stuff. So it'll make more sense when we apply those. Else, guys, that's the end of this lecture. Have a great day. Email me if you have any questions. Else, I'll see you in class.